Okay, and the first talk in this session is Matt Brown, who's going to talk about something that just sounds frankly impossible. So hopefully he'll explain that, and we'll believe him by the end. Thank you.
All right, here's hoping. Okay, thank you very much. So yeah, in this work, me and my advisor, Jens Paulsberg from, hello? Can you hear me? Is that better? Okay. So, I should say, this is joint work with my advisor, Jens Paulsberg at UCLA, and we're going to talk about our self-interpreter for F omega. So first, according to conventional wisdom, this should be impossible. No F omega interpreter can be defined in F omega itself. These two sets should not intersect. And the reason for this is that F omega is a strongly normalizing language, and the conventional wisdom is that no strongly normalizing language can have a self-interpreter. And we call this the normalization barrier. And we can find examples of this throughout the literature, from journal articles like Total Functional Programming, published 2004 in the Journal of Universal Computer Science, to books like Understanding Computation, published 2013 by O'Reilly, and even on the internet, on web pages like the wiki page for normalization. And we show that this conventional wisdom is wrong. In fact, we can define a self-interpreter for F omega. So in this talk, first I'm going to talk about where this conventional wisdom comes from and why it turns out to be wrong. And then I'll describe how we represent F omega terms in F omega and summarize our results. So the conventional wisdom is based on a theorem from computability theory that states a total universal function for the total computable functions is impossible. And we can draw parallels between universal functions and self-interpreters, and between total functions and strongly normalizing programs. And we make a similar argument to conclude that a self-interpreter for a strongly normalizing language is impossible. Okay, so now some definitions. We say that U is a universal function if, when given a code for some other function, which we denote here, this f bar is the code for a function f, and an input v to that function, the universal function computes the result of f of v. Specifically, the code for f is some number called a Gödel number. Now, if we jump over to F omega, talk about self-interpreters, we say that U is a self-interpreter for F omega if, when applied to the representation of a term, it evaluates back to that term. So in other words, a self-interpreter recovers a term from its representation. And now E bar in this context denotes a representation of a term E according to some representation scheme. So we can prove that there is no total universal function. And the proof is by contradiction. First, suppose that there is a total universal function. Then we can define another function P that takes as input some code and uses the universal function to apply the function that that code encodes to its own code. So maybe a little more clear. It takes the code for some function and uses the universal function to apply that function to its own code, and then just adds one to the result. And since the universal function is assumed to be total, this function P is also total. And now we can apply P to its own code, and we call this a diagonalization gadget. Since P is total, it is defined on its own code, so it's equal to some number n. But according to the definition of P and the definition of the universal function, we have that the diagonalization gadget is equal to 1 more than itself. And so there's a number that's equal to 1 more than itself, which is a contradiction. So we've proven that there's no total universal function. Now let's jump back over to f omega and try to apply the same argument to show that there's no self-interpreter for f omega. And again, we're going to argue by contradiction. So suppose there is a self-interpreter for f omega. Then we will define a lambda term p following what we did before. It's going to take an input x, which is a representation of some term, and use the self-interpreter to apply that term to its own representation. And then we add this lambda abstraction over an unused variable y, which plays the same role as the +1 in the previous version. And we can construct a diagonalization gadget here by applying P to its representation again. Now, we need to show before we can continue that this diagonalization gadget is still in f omega. And at this point, we're unable to do this because we haven't specified enough about what the type of the interpreter is, the types of representations, type of P, etc. So we're stuck. But we've arrived at an important question. Is it always the case that we can use a self-interpreter for some language to construct a diagonalization gadget in that language? And this is important because it's not inherently the self-interpreter that leads to non-normalization. It's the ability to define this diagonalization gadget. So if the answer is yes, then indeed f omega does not have a self-interpreter. So we can prove this formally by stating if f omega does have a self-interpreter, then it's a kind of self-interpreter that cannot be used to diagonalize or build these diagonalization gadgets. And now we continue the proof that we were working on before with this additional assumption that the diagonalization gadget is in f omega, again, leading toward a contradiction. So, since f omega is strongly normalizing, this diagonalization gadget has a normal form. We'll call that n. But by definition of our term p and the self-interpreter, the diagonalization gadget is equivalent to itself with the extra lambda abstraction over the unused variable y. Therefore, there exists a normal form n that's equivalent to lambda yn. And there's our contradiction. So the conventional wisdom goes wrong by relying on an unstated assumption that every self-interpreter can be used to construct a diagonalization gadget in that same language. And this leads to the incorrect conclusion that f omega does not have a self-interpreter. And we show this assumption to be false, specifically by using a typed representation and a typed self-interpreter, we can make diagonalization untypable. And now, what I mean by typed representation is that we represent terms of different types as representations of different types. And now a typed interpreter for one of these representations is going to be polymorphic in the type of representations. And this is good news more generally because typed representation has been shown to make metaprogramming less error-prone, and it's also been shown to be useful for defining self-interpreters for statically typed languages. So Whether a self-interpreter for f omega is possible depends crucially on how we want to represent f omega terms. If we tried to represent them using something like Gödel numbering, where every term is represented, where every term is represented by some number of type nat, for example, then such a hypothetical self-interpreter could be used to diagonalize and contradict the fact that f omega is strongly normalizing. So that won't work. But if we use a typed representation and a typed self-interpreter, we get a self-interpreter for f omega. Okay, so now I'll talk about how we represent f omega terms in itself. So what we want is a typed self-representation of f omega, which is going to consist of a quotation function defined somewhere else outside of f omega that maps terms to their representations. And we have some requirements here. Every closed term in f omega should have a representation, and that representation should also be a closed term in f omega. And we want quotation to be injective, so that no two terms have the same representation, and this requirement rules out some opportunities to cheat. Representation should also be data, which for us means lambda terms in normal forms. And we want our representations to support folds. We want to be able to fold over the representations. So we can apply standard representation techniques, but there's a key challenge, which is how to represent polymorphism in terms. Particular type abstractions, sometimes called generalization in other languages, and type application, sometimes called instantiation. So previous work used what we call an intentional approach to representing polymorphism. The idea here is to decompose a quantified type into a kind of the quantifier, and a type level function corresponds to the body of the quantifier. And if we do this, if we have both of these things, then this together describes the complete set of instantiations of that quantified type. The problem with this approach is that it relies on kind abstraction in order to abstract over these two parts. And kind polymorphism is outside of f omega. So this won't work for a self-representation of f omega. So instead, we develop a novel extensional approach to representing polymorphism that focuses on the relationship between a quantified type and an instance of that type. And we witness this relationship using small instantiation functions. We found that it's sufficient to only witness the instantiations that are used in a particular term. So we don't need to encode the entire set. And most importantly, we get something that we can use in f omega. Doesn't require any additional power. So to summarize the difference between these two approaches, the intentional approach characterizes the entire set of instantiations, which turns out to be more information than necessary. And by focusing only on the instantiations that we care about to represent a particular term, we get something that we can use in f omega. So our self-representation consists essentially of our extensional approach to representing polymorphism and standard representation techniques for lambda calculus, specifically parametric higher order abstract syntax based on church encoding. So results. First, despite conventional wisdom, we break through the normalization barrier by defining a self-interpreter for f omega. Our main result is a deep self-representation that supports folds, and we program 5 folds. A self-interpreter, a measure of the size of a term, a typed continuation passing style transformation, a simple structural predicate is-abs, and a normal form checker. We also show a shallow typed self-representation, which is kind of the simplest thing that we could come up with if we ignore the requirement to support folds. The representation only supports the interpreter, no other operations, and that interpreter is not defined as a fold. But the technique also works for other languages like System F or F omega plus, which extends F omega with kind polymorphism. So some theorems. First, every closed F omega term can be represented as a closed F omega term. Representations are also beta normal forms, and quotation is injective. Here is our self-interpreter for the deep representation, defined as a fold. And this slide is intended just to show that it's relatively small and not too complex. And full details are in the paper. So some theorems about our interpreter. First of all, it's a closed F omega term. It's well typed, and it's correct. So it recovers any term from its representation. In particular, it can correctly interpret its own representation. So we have an artifact available from our website, which includes an implementation of F omega with syntactic support for defining representations, as well as a type checker, evaluator, equivalence checker, and many examples of our metaprograms. We also have an appendix containing proofs of all of our theorems, also available from our website. So we fit into the broader tradition of typed self-interpretation, which goes back to Fenning and Lee in 1991, who first posed the question of whether System F or F omega could have a self-interpreter. And they were using the intentional approach to representing polymorphism, and so they didn't quite get the self-interpreter, but they did show a representation and interpreter for System F and F omega, and for F omega and F omega plus, which again extends F omega with kind polymorphism. The first self-interpreter for a statically typed language was presented in 2009 by Rendell, Osterman, and Hofer, and that was for a lambda calculus with the kind-in-kind rule that made type checking undecidable in the language, not normalizing. 2011, Jay and Paulsberg presented a typed self-interpreter for a statically typed combinator calculus. And last year at Popple, we presented the first self-representation for a language with decidable type checking, Girard's System U. And so this figure puts our results into context. So here the normalization barrier separates the three strongly normalizing languages on the left from the non-normalizing System U on the right. And we contribute the three self-loops to the left of the normalization barrier, denoting the first self-interpreters for strongly normalizing languages. Again, for F omega, we have a deep self-representation that supports folds. And for System F, F omega, and F omega plus, we have this shallow representation, which just kind of demonstrates that something is possible with the simplest requirements. So, as I said earlier, typed representation more generally can make metaprogramming less error-prone. For example, it can ensure only well-typed programs can be represented, so metaprograms can't introduce type errors. And it can prevent metaprograms from getting stuck. And we can get some strong correctness properties of metaprograms. For example, that an interpreter or an optimizer preserves the type of its program. And there's a lot of different ways of achieving a typed self-representation, from church encodings for lambda calculus, which is similar to what we use, to dependent inductive types for languages like Agda or Coq, to GADTs or tagless representations for Haskell and ML. So related to typed metaprogramming is mechanized meta-theory, the goal of which is to machine check proofs of meta-theorems about a particular language. And this is usually done by defining a representation of that language in a proof assistant based on type theory or higher order logic. And there's been a long-standing goal to formalize parts of type theory in type theory. And we can relate that goal to the goals of self-representation and self-applicable metaprogramming, self-interpreters. But mechanized meta-theory requires a lot of expressive power in order to prove deep properties like type soundness or normalization. And that results in a relatively large gap between the meta-language and the object language. Metaprogramming can get by with less expressive power, and even for strongly normalizing languages, we can reduce the gap between the languages to 0. We can get a self-representation. Okay, so to conclude, we showed the first self-interpreter for a strongly normalizing language, F omega, and this solves a problem first posed by Fenning and Lee in 1991, highlights the need for better terminology to distinguish between what's possible and impossible in strongly normalizing languages, and we have some new techniques that provide new opportunities for type-checking self-applicable metaprograms. Thank you.
Hi, Greg Morissette. Quick question. So, first of all, cool paper.
Thank you.
Second of all, so you're using beta normal forms as a representation?
I'm sorry?
You're using beta normal forms for the representation, you said?
Yes. So specifically, it's a church encoding, higher order abstract syntax. Yeah.
So I mean, in a practical sense, then you're evaluating the program when you quote it, right? And so from a practical sense, is it a really useful meta interpreter?
You're saying we evaluate the program when we quote it?
Yeah,
So,
I mean, you're normalizing it.
No.
Right?
We don't do any evaluation of the original term, but the thing that we construct doesn't have any readexes because we put variables in all the places. So
I see. Okay, thanks.
Excuse me. Yes. Sorry about that.
Phil Wadler, University of Edinburgh. My head is well and truly exploded. I'm still picking up my pieces of brain from the floor. So I'm trying to work out what this means. So one thing you point out is that if we represent terms by Gödel numbers, then there is no self-representation.
Right.
But I think that means that if you had a mapping from your representation to a Gödel number representation, that would show that that mapping could not exist. Am I right that that's where trying to make the proof fall down by taking your representation and mapping it into Gödel numbers would not work?
I am not sure about that. I think the important thing is that we have this extra step that we have to do in F omega, which is make sure that the diagonalization gadget is typed. So if we were in Gödel numbers and there was some way of expressing that check and say, doing something similar there, but I don't know if something like that makes sense.
So I'm guessing that I could just turn your proof that there is a self-interpreter for this representation into a contradiction, either by using a mapping from your representation to Gödel numbers, or possibly we need the inverse. But it should be relatively easy to construct that proof, and that would then show that one of those two mappings must not exist. Have you tried to do that exercise?
That sounds interesting, yes.
I think that might give some additional insight. In particular, the fact that one or the other of those is not representable, I would find surprising.
Right.
So it would be worth carrying that through.
Thank you, yeah.
Hi, I'm Thorsten Altenkirch. First of all, very nice result. I'd like to congratulate you for this. I'm wondering a bit, we have all these papers and even Wikipedia saying something which seems to be wrong. Yeah? Are you now suggesting that we're going to change this or rip these pages out of all the books? Or I'm wondering, maybe that's an alternative, because somehow my feeling is that intuitively these arguments are somehow right, and maybe it is that the specification of what's a self-interpreter lacks something, because for me a self-interpreter should allow me to do diagonalization.
Mm-hmm.
So maybe
Yes.
there's something which needs to be added to the specification of a self-interpreter. Have you
Right.
thought about
So,
this?
yeah, I think the authors of those quotes, when they say self-interpreter, they mean for something like Gödel numbers. But the key thing is that in the PL community, self-interpreter and self-representation, these things have much broader meanings. And once we have higher order abstract syntax and we have typed representation, then if we are calling those things self-interpreters, then that's contradicting what these people are saying about Gödel numbers. And so we just shouldn't all be using the same words. So we need more precise terminology to distinguish between these different ideas. Up until now, there hasn't really been a need to do that because everyone thought that there was no evidence that there was really any big difference between all these techniques. But now we've shown that there is.
I mean, maybe we can add something to the specification of a self-interpreter you had, which would rule out your self-interpreter, right?
Sure. Thank you.